Bon. Merci de votre invitation. C'est un grand plaisir de retrouver l'Institut Fourier, d'avoir contribué à ma mesure parce que l'analyse continue à vivre dans ce journal. Je ne suis pas le seul, évidemment. Et puis, plaisir de retrouver quelques têtes connues, plus anciennes et plus jeunes. Donc, je vais vous parler de transformation de Fourier, justement. Transformation de Fourier non linéaire. Associée à une équation non linéaire également, qui s'appelle l'équation de Benjamin-Ono. Alors, qu'est-ce qu'il y a derrière? S'il y a derrière, c'est une notion que souvent on nomme intégrabilité. Il y a un certain nombre d'équations ou dérivées partielles dans le monde de la physique mathématique, souvent, qui ont cette propriété d'intégrabilité. On ne sait pas exactement très bien la définir, mais il y a un certain nombre de symptômes, disons. Bien, alors, si vous connaissez, si vous avez peut-être entendu parler, même les plus algébristes d'entre vous, et pour cause, de l'équation de Korteweg de Vries, par exemple, qui est une équation qui vient de la mécanique des fluides, eh bien, elle a ces symptômes-là. Hein, elle a une transformation de Fourier non linéaire. Alors, je voudrais vous présenter sa petite sœur. Elle s'appelle l'équation de Benjamin-Ono. Elle a des propriétés du même genre, mais en un certain sens, et je vais essayer de vous dire pourquoi, elles sont plus faciles à manipuler. C'est une transformation de Fourier non linéaire, donc, qui est plus agréable à manipuler. On va voir pourquoi. En un certain sens, elle est plus explicite. Bon, alors, qu'est-ce que c'est que l'équation de Benjamin-Ono? Je ne vais pas faire de modélisation ici, j'en suis d'ailleurs incapable, mais sachez quand même que la première fois que cette équation est écrite, c'est dans un article du Journal of Fluid Mechanics en 1967 par Brooke Benjamin. Et en gros, eh bien, vous avez deux fluides, bon, de l'eau et de l'air par exemple, qui sont soumis aux forces de gravité, qui sont irrotationnels, incompressibles, et puis on regarde l'interface, donc une vague, par exemple. Alors il y a des hypothèses évidemment pour se simplifier la vie, parce que l'équation elle est assez compliquée si on l'écrit comme ça. D'abord, je suppose que je suis dans un plan et pas en 3 dimensions. Ensuite, je suppose que la profondeur de ma mer est infinie. Et puis, je suppose que la taille relative de l'interface, de la hauteur de l'interface, est petite par rapport à la taille transversale comme ça. Bon, il y a toutes sortes de choses. Si ça vous intéresse, il y a une dérivation plus précise et plus mathématique qui a été faite par 3 mathématiciens, Jerry Bonna, David Lann et Jean-Claude Sau, dans les années 2000. Mais si vous appelez U la déformation par rapport à un axe horizontal de votre vague, eh bien, ça fait une fonction de 2 variables, le temps, et puis justement l'abscisse sur l'axe horizontal, et vous avez une équation comme ça. D rond U sur D rond T égale la somme de 2 termes. Alors, il y en a un qui est non local, H D2IU sur DX2. Je vais expliquer ce qu'est H. Et puis, il y en a un qui est non linéaire, mais local, moins D sur DX de U carré. Voilà l'équation de Benjamin-Ono. Donc, encore une fois, U est une fonction de 2 variables, T et X, à valeur dans R. H, c'est quoi? C'est ce qu'on appelle la transformation de Hilbert. Alors il y a des raisons pour que cette transformation de Hilbert intervienne, parce que, et ça le fondateur de des annales de l'Institut Fourier le savait bien, parce que c'est de la théorie du potentiel. Hein, cette transformation, quand vous résolvez l'équation de Laplace dans un demi-plan, hein, et vous donnez des conditions de Dirichlet, hein, la trace de votre solution sur la droite frontière de ce demi-plan, eh bien, la transformation de Hilbert va intervenir dans l'expression de la dérivée normale. Hein, d'accord. Eh bien, cette dérivée normale, hd sur dx, elle intervient là. Hein. Et c'est pour ça, parce que comme on a des fluides incompressibles irrotationnels, en fait, on résout des équations de Laplace. Voilà. C'est exactement pour ça. Alors, cette transformation de Hilbert, ben, ça dépend. Il y a essentiellement deux cadres. Soit vous travaillez avec des fonctions, votre espace des phases, c'est-à-dire l'espace des fonctions en x. Il faut vraiment penser ça comme une déformation au cours du temps d'une fonction de x. Eh bien, système dynamique, si vous voulez. Eh bien, soit vous pensez à un espace de fonctions qui sont suffisamment décroissantes à l'infini, par exemple, pour être L2, hein. Soit vous, au contraire, vous allez penser à des fonctions qui sont périodiques en x. Disons 2π périodiques. Alors, moi, je vais me placer dans ce cadre-là, parce que c'est plus facile, en fait. Et parce qu'on a des résultats beaucoup plus généraux et beaucoup plus complets. Dans ce cas-là, évidemment, la transformation de Hilbert, vous pouvez la définir à l'aide de la théorie des séries de Fourier. Donc, si vous définissez le coefficient de Fourier d'une fonction périodique, comme d'habitude, enfin comme Fourier, plus exactement, à peu près, eh bien, la transformation de Fourier, le coefficient de Fourier de la transformation de Hilbert, de la transformée de Hilbert, HF, c'est quoi? C'est simplement moins i, signe de k, fois f chapeau de k. Voilà. C'est la fonction signe, vous mettez un facteur i devant pour que ça fasse quelque chose qui est anti-adjoint, et h carré égale moins l'identité. Hein? Bien. Alors, pourquoi cette équation nous intéresse tant? Ben parce que justement, comme je l'ai dit, elle a ses propriétés d'intégrabilité, on va le voir d'un peu plus près, mais avant cela, je voudrais quand même motiver mon propos, hein, notamment pour les gens qui ne connaissent pas trop les équations dérivées partielles d'évolution. Eh bien, quel genre de questions on se pose sur une équation comme ça? Quelles sont les questions naturelles? Alors, première question, c'est évidemment... Hein, oh, I'm sorry, I should switch to English. You forgot to tell me. Oh, I'm sorry. But because I will tell you why I thought of English now. Because I wanted to state a notion, a concept which is much easier to state in English, which is well-posedness. Try to translate well-posedness in French. It's impossible. C'est un problème de Cauchy bien posé. Well-posedness of the Cauchy problem. Okay? Un problème bien posé. We need to use several words in French, while in English, okay, so this is English. Questions? So, and well-posedness of the Cauchy problem. Sorry. What does that mean? It means that you assume that you have a function, you know the function at t equals 0, and you want to determine u at time t for every t. Okay? So does it exist? Is it unique? In which space, in which functional space is it possible? So, second question, so this is, of course, some people will tell you that, okay, we know it comes from physics, so the solution should exist, but that's not so easy. I mean, the second question is, assume that everything is well posed and well defined for every time, which will be the case here. What happens for long time? Long time behavior. This is really the interesting question from the dynamical system point of view, of course. How does it behave? And the third question, which is in fact connected to the second one, is, do you know any special solutions? Special solutions in such situations of Hamiltonian systems are sometimes called traveling wave solutions. And here, traveling wave solutions will be solutions of the kind u of tx equals u naught of x plus ct. So at t equals 0, u of 0x is u naught of x, but the solution is just obtained by adding to the variable x a constant times t. And t is, of course, the velocity. And so, can you characterize all that kind of solutions? Usually, if you plug this expression u0 of x plus ct into the equation, you get an elliptic equation, which is not so easy to solve. And secondly, are they stable? In which sense? I mean, assume we have such a traveling wave solution, and imagine that now you consider an initial datum which is very close to it. So we make a small perturbation. So again, it's a question of dynamical systems. Small perturbation of this. So in general, you will not have a traveling wave solution again, but you may expect that the solution stays close to, well, not exactly the solution itself, but what we call the orbit of this traveling wave, which is the set of all translations of translated of u0, u0 of x plus a for a river, which is called, this is called orbital stability, which is the most natural stability notion. So can we answer these questions for this equation? And what I'm going to tell you today is yes, completely. But before telling you this, I'm going to start with something much simpler, which is looking at this equation. So you have two terms here. In some sense, they are in competition. If you forget this term, you get an equation that people in fluid mechanics know very well. This is called the Burger's equation. This equation will not have global well-posedness. If you start from a function which is smooth, for a finite time, you might have some breakdown of the solution. Okay, you can define some flow map with weak solutions, but it's not so easy. This is Korshkov theory. But okay, so this is that kind of equation. Now, if you forget about this term, the nonlinear term, you will get a constant coefficient equation. And here we have, of course, the tool of Fourier transform. And the tool of Fourier transform is going, in fact, to answer these questions for this much simpler linear solution, linear equation, sorry. So let's look at, just as a warming up, let's forget about, for a short while, let's forget about the nonlinear term. If I write this equation here, and if I look at the Fourier transform, namely the Fourier coefficient of u at time t, then this equation becomes a very, very simple ODE, which you can solve like this. Okay, so this is very easy. But what I wanted to tell you is that it answers immediately the three questions here. Well, posedness. Well, essentially, if I'm given, for instance, a function which is smooth, u0, then of course you will have a u which is smooth, because you can characterize smoothness by Fourier coefficients. If I take just a distribution, then I'll have a function, a nice function of time valued in distributions. And in between, you will have Sobolev spaces, which is precisely this set of functions such that for every S in R, you can define distributions such that this series is convergent. So for S equals 0, this precisely corresponds to the L2 functions by the Parseval formula. And if I'm taking u0 in such a space, then u will be in the same space. And moreover, this norm will be conserved here. So what is interesting here is that, for instance, the second point here, the answer to the second point will be that u, the function t, u of t, in HS, is almost periodic. Of course, because, well, that's precisely the notion of almost periodic function. So it corresponds to enrolling a line on an infinite dimensional torus. And this is nice because, for instance, it implies Poincaré recurrence theorem, which tells you that for any given initial datum, there will be a sequence Tn going to infinity such that u of Tn converge to u0. So you can come back very close to your initial datum infinitely many. This is, of course, a consequence of this representation. And what about the second question? Well, the second question is very easy because you have a very nice additional property of the Fourier transform, which tells you that if you translate a function by a parameter a, this precisely corresponds to multiplying your Fourier coefficient by e to the ika. So as a consequence, if you compare the expression of the Fourier transform of u0 of x plus ct and with this, we immediately find that traveling waves are what I call unimodal. In the sense, at least on the, if I'm working with real valued functions, say unimodal, if I look only at Fourier modes which are at least one, well, just because you will have u0 of k e to the I kct equals u0 of k e to the I t k square sine of k. So you see, the only possibility is that C is k sine of k for some k if u0 of at of k is non-zero. But since this, which is absolute value of k, by the way, since this is clearly on k at least 1 an injective function, it tells you that the only u0 such that u0 of k is not 0 is reduced to 1k, which is this one. So you characterize the traveling waves, and you can prove, for instance, that these traveling waves are stable in this sense. Okay. Okay, this was extremely elementary, but I wanted to just to make this as a tribute to Fourier. And now, the nice thing is that we can essentially do the same thing with this nonlinear equation and answer the same kind of questions. So the theorem I would like to state now is the following. So this is a theorem that I proved with Thomas Kappeler. And there is a more recent paper with another collaborator called Peter Toeplitz. And it tells you this. There exists a nonlinear Fourier transform. So there exists a mapping, capital Phi, which sends the union of Sobolev spaces valued in R, but only for S strictly bigger than -1/2. I will tell you why. I'm going to add one thing here, one additional constraint. It's not a big deal. I will put a 0 for telling you that I'm working with function with average equals 0. Average equals 0 for such an equation is not a big deal because the average of u on x is conserved. It's a conserved quantity. People who know a little more about Hamiltonian systems will see that we are, in fact, a very special conserved quantity, which is sometimes called a Casimir function. Okay, Casimir functional. Okay, so essentially we can forget about this, as it was, in fact, also for the Fourier transform, for the linear part. Valued in what? Valued in a set of sequences. So I'm going to define a set of Fourier, nonlinear Fourier coefficients, complex numbers, such that there exists an S bigger than 1/2, such that sum of n1 plus 2s zeta n square converge. And in fact, this S will correspond. So this is the first property. So this is bijective, but in fact it's even better. Phi from HS0 to this space here. Oh, sorry. HS plus 1/2. So this is the space of sequences such that sum of n plus 2s zeta n square. So these are really Fourier coefficients of some Sobolev functions, if you like, in h1/2 plus s. This is our homeomorphism. First point. Second point, this homeomorphism allows you to trivialize the evolution of this equation. What does that mean? It means that, okay, people worked on this equation, I forgot to tell you. They have been working on it for about 40 years. The first rigorous results about global well-posedness for smooth solutions are due to Jean-Claude Sau in 1979. But then many people worked on that, trying to improve this well-posedness theory, saying, okay, is it well-posed in L2, in some other space, Sobolev spaces, etc. So up to 2008, I mean, people like Tao, like Koenig worked on that, whatever. And here I would say, if I take an initial datum U0 in HS. So remember, S is bigger than 1/2. So U0 can clearly be a distribution, not a function. Then you see, given a meaning to this equation is not so easy if U is not in L2. Because U square, what is U square if U is a distribution? Well, I claim that even in that case, I can give a meaning just by saying that the flow map can be extended by continuity. So, in other words, there is, for every sequence of data, let's say C infinity, which converge to U0 in HS, then the corresponding solutions will converge to some function in HS for every t. And this function can be characterized by phi. How? Exactly as we did for the Fourier coefficients, in the sense that if you look at zeta n of u at time t, that's exactly zeta n of u0 times e to the it omega n of u0. So this omega n is like the k square sine of k we had in the Fourier analysis. The very nice thing is that the omega n's, they depend on u0, but you know exactly how. You have an explicit formula which I will give you now. So it's n squared. So n squared would be exactly what you would get for the linear equation. But now you have a nonlinear perturbation, which is this one, minimum of k n zeta k of u0 square. So if you know a little bit of Hamiltonian systems and integrable Hamiltonian systems in the sense of Uville, essentially the mod square of the zeta n's are what we will call the actions. The actions will be conserved, of course, by the evolution, since if you take the modulus square of this, it does not depend on t. And these actions will provide you with frequencies which tell you exactly how the angles are moving. And they are moving with a constant velocity, which is this one, very explicit. So if you know a little bit about KdV, and if you don't know, let me refer to the beautiful book by Kappeler and Pöschel in Springer, which is called KdVNKAM. Okay? It's a beautiful book. If you look at the first chapters, you will see a presentation, a very pedagogical representation of the construction of a nonlinear Fourier transform for KdV. You will see that this expression, of course it exists, but the expression here is terrible. In fact, it's very, very non-explicit in terms of the zeta-n's. Here we have something extremely simple. And what should I say more? Oh, yes, of course. The third question, the third point is that if I take now a translation, now that's a miracle, but it's still exactly the same formula as Fourier. So this mapping is very nonlinear. I will tell you how to construct it, of course. But before telling you this, I would like to address the three questions above. So first question, well-posedness. Well-posedness in HS for every s bigger than a half. For every u0 in HS for s bigger than a half, I can solve this equation in some sense, in the sense that I can, again, extend by continuity the flow map, and have some uniqueness among, of course, the functions which are well approximated by smooth functions, which is a nice definition of weak solutions. I mean, you approximate by smooth data, and the solution is approximated by the smooth solutions. So this is a new result. In fact, people were only able to prove it for L2, up to L2, because they needed, in some sense, the expression of the equation to prove it. So here we can go much further. Second, everything is almost periodic. Solutions, HS solutions, are almost periodic in HS for every s bigger than a half. So just to tell you, people tried to prove the Poincaré recurrence theorem. It was, for instance, you have a very nice review paper by Nikolai Zvetkov in 2014 in Journée of PDEs in the new Saint-Jean-de-Mont, okay? And they prove some statistical property. So they were able, so there is Zetkov, Vishilia, and another guy called Yu Deng, Vishilia Deng. So it's a Bulgarian, Italian, Chinese collaboration. And they prove that you can define Gibbs measures on a set of functions which are smooth enough, on which, so Gibbs measures are measures which will be essentially invariant by the flow, and almost surely for these probability measures, the flow map will have this recurrence property of Poincaré. But they were only able to prove it almost surely, and moreover with S big enough, okay? And they were asking about this question of almost periodicity and Poincaré recurrence for all S and this answers completely their question. And third, special solutions. Well, you play exactly the same game as we did with Fourier. And you say that you obtain that traveling waves are unimodal states corresponding to this u such that zeta n of u equals 0 except for one n. For the same reasons, because omega n divided by n is a strictly increasing sequence. It's very easy to see it. Okay? It's strictly increasing. Okay, so, and moreover, you can prove, so these traveling waves were in fact already characterized by a completely different method using complex analysis by Amick and Toland in 1991 in a nice paper in the ACTA. And in fact, you can recover this by this method plus some inverse spectral formula, ISF, okay? Inverse spectral formula. Phi minus 1, in fact, has some explicit formula. Complicated, but explicit. And then you will see that these guys, the traveling waves, are essentially the Poisson kernels. So you take a kernel, 1 minus r square, 1 minus 2r cosine x, so you put an n plus r square, you multiply by n, minus n in order to get average equals 0, and these are the traveling waves. Just this. Okay? And you can recover that. And they are the only ones. And moreover, they have orbital stability for the same reasons. Okay, so this is, of course, completely included as very easy consequences of this theorem. So now in the rest of my talk, I would like to explain how to construct such a field. And this is spectral theory. Okay, so so for this, you need an additional structure, which is a very rich structure about this equation. And this structure is called a lax pair. What is a lax pair? A lax pair is a way to associate to any state u, don't forget about functional spaces. Think of u C infinity, if you like, okay? To any state u, C infinity periodic, real valued, an operator Lu, which is self-adjoint, say, on some Hilbert space. some auxiliary Hilbert space. And this LU will have the property that if you solve the equation, our Benjamin-Ono equation, then LU remains unitarily equivalent to LU at time 0. U of t is unitary. Of course, unitary on this Hilbert space. Okay? And as a consequence, the spectrum of LU at time t will be a conservation law. So in this special case, so in KdV and many other classical integrable equations in the mathematical physics, LU is in general a differential operator. For instance, for KdV, LU is just the Schrödinger operator, minus d squared dx squared plus u. There is a nice talk by Yves in Bourbaki seminar a long time ago about that. Okay? And but here, LU will not be differential. LU is non-local, and it's what we call a Toeplitz operator. So what is the Hilbert space? First, the Hilbert space is called the Hardy space on the circle. So these are functions L2 on the circle such that the Fourier transform associated to any negative Fourier mode is 0. If you prefer, these are holomorphic functions on the disk which have a trace in L2 on the circle. Okay? So you identify these functions, these holomorphic functions, to their traces. So this is H+. Now, of course, this H+ is endowed with a nice projector, which is sometimes called Ries projector, sometimes Zeger projector. I prefer Zeger. Zeger projector, which is the orthogonal projector from L2 to H+. And this is very easy. It sends a Fourier series with any modes to the same Fourier series where you forgot the negative Fourier modes. Okay? Just that. And now I'm going to define LU. So I pick a U function. I should first maybe define what is called the Toeplitz operator of symbol B in L infinity of t. Toeplitz operator, TB, is just the linear map from H+ to H+, which sends a function f to pi of BF. It's a bounded operator. It's very easy to see that it's self-adjoint if and only if B is real valued. Okay? And now my LU is what? My LU is just 1 over I ddx. So remember, 1 over I ddx corresponds exactly to spectral theory. I mean, the eigenfunctions of this are precisely the guy of Fourier series. Okay? Now I perturb it by TU. So U is real valued, so TU is self-adjoint, and it's rather easy to prove that if U is smooth enough, LU is self-adjoint. It's less easy to prove that using the form theory, that if U is in HS for S bigger than -1/2, it's still self-adjoint. It's a consequence of a nice paradifferential identity due to Boni, which tells you that if you have two functions f and g in HS in one variable, say on the circle, f in HS and g in HT, and you put s and t between 0 and 1/2, but s plus t bigger than 1/2, then fg is in HS plus t minus 1/2. It's an exercise in paradifferential calculus for people who like it. Okay? So you use this to prove that the form LU of fg on some Sobolev space intersected with the Hardy space is well defined, and you can define a self-adjoint operator as soon as U is in HS for S bigger than a half. Now, what do you do with that? Now, not only LU is self-adjoint, but you can in fact prove that LU has compact resolvent, because we are on the circle. And so on the circle, we have the Relish theorem, which tells you that if S is positive, HS has a compact embedding into L2. Relish theorem, compactness theorem. So LU has compact resolvent. And so the spectrum of LU is made of a sequence of eigenvalues which will go to plus infinity. Why? Because 1 over I ddx, because we are on H plus, 1 over I ddx has a spectrum which goes only to plus infinity. The spectrum is just k for k at least 0. So the spectrum of LU is something like this. Lambda 0 of U, lambda 1 of U, etc. Lambda n of U. Now, the nice thing is that, in fact, this spectrum is simple. The inequality is straight. So if you prefer, the eigenvalues are simple. In fact, there is even better. You can prove that the difference between two consecutive eigenvalues is always at least 1. And you can define an object, which I will call gamma n, which is lambda n of u minus lambda n minus 1 of u minus 1, which is non-negative. This, we will call it the nth gap. Why? So those who know a little bit about spectral theory of operator with periodic coefficients, what is called Floquet theory or Floquet-Bloch theory, they heard about this notion of gaps. And this theory is what? Okay, so you have an operator like this, like LU. You can think of it in two ways. Either you think of it on an operator on periodic functions. That's what I did, okay? But you can also think of it as an operator on L2 of the line of R. And it's in fact possible because you can define pi on the line as well. Now, it's another operator. In that case, the spectrum is not, of course, discrete at all. It's made of what people call bands, which are, in fact, intervals. It's a continuous spectrum with intervals. In this special case, the bands are exactly length 1. And they are the bands lambda n of u plus 1. And so the difference between the two bands, the distance between the two bands, so you have here the band lambda n minus 1 of u, lambda n of u, lambda n minus 1 of u plus 1, and the next band is lambda n of u plus 1. The difference between these two bands is precisely our gamma n of u. So the gap is just the gap between the two bands. You can interpret them like this, okay? And to prove that the bands are length 1, you just do Floquet decomposition. It's not difficult. For people who know Floquet decomposition, it's really easy. For those who don't know, never mind, okay? We just have these lambda n's, and now I claim that we have nice properties about these gamma n's. What are the properties of these gamma n's? Well, for instance, we have a Parseval formula, maybe the most striking thing. U in L2 square is just twice the sum from n equals 1 to infinity of n gamma n of u. So I repeat this. You look at this operator. You prove it has compact resolvent, simple spectrum. You look at its eigenvalues. you look at the gaps between eigenvalues in this sense. You know that they are non-negative. And in fact, if you compute this, you get UL square. You have other formula of that kind. But in general, so what you can prove, I don't have too much time, but what you can prove is what? You can prove a complete theory of inverse spectral theory, in the sense that, for instance, if you're giving me a sequence gamma n, maybe I should say that U is in HS in general is equivalent to sum of n to the 1 plus 2s gamma n of U is finite for every s bigger than minus of. And you, of course, bounded subsets. Okay? So you don't have such a nice identity which is only for s equals 0, but for every s you have correspondence. And now you can, in fact, prove that if you give me a sequence gamma n of non-negative numbers such that there exists an s bigger than 1/2, minus 1/2, such that n plus 2s gamma n is finite. And I can tell you exactly what's the structure of the isospectral set. So what's the isospectral set? So gamma, iso of gamma is just the set of U's such that the spectrum, the gamma n of U are gamma n for any n. Theorem, iso of gamma is a torus. In fact, it's a Lagrangian torus, in the sense I don't introduce the notion of the symplectic notions, but in fact there is some Poisson bracket. There is a Poisson bracket on functions of U. If I have two functions of U, real value, then smooth enough, I can define a Poisson bracket, which is another function of U, which is exactly given by the formula 1 over 2 pi integral from 0 to 2 pi dx of the gradient of U with respect to U of U and gradient with respect to U of G. Gradient with respect to U, think of functions on L2, smooth. So they have a differential, so they have a gradient which is induced by the L2 structure. So the gradient is an L2 function, and now in good cases you can give a meaning to this integral. This is the Gardner bracket, Poisson bracket. Okay, so what I claim is that this is a torus which is Lagrangian for this Poisson bracket. And now, what's the connection with my Fourier transform? That's very easy. What is phi of U? What are the zeta n of U? Zeta n of U is what? 0 if gamma n of U equals 0. And square root of gamma n of U e to the I phi n of U, where phi n of U is the argument of it's minus the argument, in fact, of the integral of fn of U dx. So what is fn here? That's just the eigenfunction corresponding to lambda n. So you make it of norm 1. And of course, it's not sufficient because they are complex functions. So you have some angle to be defined. And there is a way to make them completely defined in a very smooth and analytic way, which is that the fn's, so you can demand that f0 times 1 is positive, and fn times e to the ix fn minus 1 is positive for all n. And here there is only one choice of eigenfunction for that. And now you look at this integral. It's never 0 if gamma n is different from 0. This is a lemma. And you can define your zeta n that way. So look, the zeta n square, the actions are precisely the gamma n's. So we are in a spectral theory where the actions are precisely the gaps. Exactly that. So, yes, I'm essentially done. But I don't know exactly what that we are. So, c'est pas l'heure, oui. Oui, c'est quoi l'heure? Excuse-moi parce que j'ai pas ma montre. C'est midi et quart. Midi et quart, c'est 1 heure de moins. Ok, très bien. Ok, so I'm almost done. Just one more key. There is in fact a deus ex machina in all this theory, and this is very specific to the fact that we are working on the RD space. On this RD space, there is an operator which is extremely important, and this is known for a long time, at least for Berling theorem. And this operator is called the shift operator. The shift operator on the RD space is something extremely simple to define. It just consists in multiplying by e to the ix. And it's called shift operator because the result of this on Fourier transform is just a shift on the right. Okay, you put a 0 in front of the Fourier coefficient. So this shift operator is extremely important. It's of course an isometry, non-surjective, but it satisfies S star S equals identity and S star equals identity minus dot 1, 1. And the connection between S and the LUs is that the LUs are precisely these operators such that S star LUS equals LU plus identity. This number here, 1, is exactly the one which is here. This one. Okay, so all these identities I wrote are in fact connected to this very important formula. And for the rest, I mean, you can look at our paper with Thomas Kappeler. You will find it on the web. Thank you very much for your attention. Eric. Yes, it is. In the sense that for every s smaller than -1/2, you can prove you cannot extend the flow map. There is still a question about exactly -1/2. For this, we don't know. But people knew that already. And it's extremely easy because you can approximate the Dirac mass, which is in h minus ½ minus epsilon for every epsilon, as you know. You can approximate it by traveling waves. And so you can explicitly compute the formula, the equation, the solution of the equation in that case, and you can prove that this solution cannot have a limit in that case. No, there is no simple way to guess it.